Hello everyone, my name is Tan Jianjie. I come from Okayama University, Japan. Today I would like to introduce my research. The title is an approach for tackling Speck on microcontroller with correlation power analysis. Here is the outline of this presentation. The first is background and purpose of this research. Internet of Things technology is widely spreading. We're now living in an information age, and IoT devices have become an indispensable part of our lives. For lightweight IoT devices, traditional encryption algorithms are very heavy on these devices. In order to ensure the security of IoT devices in communication, designing lightweight and high-security cipher algorithms that can be used for these IoT devices has become a very popular topic in the field of cryptography in recent years. Lightweight cipher has many advantages. For example, it occupies less memory, consumes less power, and it can run more efficiently on IoT devices. Here are some representative lightweight ciphers. Due to the popularity of IoT devices, side-channel attacks is becoming a serious threat to these devices, especially those unprotected IoT devices. Side-channel attack is a method of attacking an encryption device. It uses the physical information of the device and the mathematical statistics. Many previous studies have shown that some traditional cipher algorithms, such as AES, can be attacked by using side-channel attack. As I mentioned before, traditional ciphers are very heavy on lightweight IoT devices, but lightweight ciphers can work well on these devices. So, how about the security of lightweight ciphers? In this research, we propose a method based on side-channel attack that can successfully attack the Speck algorithm. The second part is fundamentals. Speck proposed by the NSA in 2013. There are 10 types of Speck algorithms according to different parameters. The block size supports 32 to 128 bits. The key size supports 64 to 256 bits, and the word size supports 16 to 64 bits. The round of encryption ranges from 22 to 34. The table here shows different kinds of Speck. The round function of Speck is shown as a figure. Here, xi and yi means left input and right input of the encryption function in ith round. Here, I starts from 0. S2 minus alpha and S2 beta means the right and left circular shift by alpha and beta bits. RKI means the round key of the ith round. The formula of round function is shown as below. The key expansion process is roughly the same as the encryption process. The difference is mainly in the first XOR position in each round. Here are some definitions and formulas of the key expansion function. Now I want to briefly introduce the power model. In CMOS circuits, power models are generally used to describe or deduce the state of power consumption in mathematical form. There are two types of power models, Hamming weight model and the Hamming distance model. Hamming weight model only focuses on a certain state to predict power consumption. Simply, the Hamming weight of a data is equal to the number of 1 in the data. So, when the circuit reads and writes data, the Hamming weight also changes with the number of 1 in the data. The Hamming distance model is generally used to predict power consumption by describing the change of circuit state within a period of time, not only focus on a certain state. In our experiment, we use Hamming weight as our power model. Next is power analysis. Power analysis is a side-channel attack method in cryptography. There are many kinds of power analysis, like simple power analysis (SPA), the visual analysis to power traces or diagrams of electrical activity over time. Differential power analysis (DPA), a more advanced form of power analysis, which allows an attacker to calculate the intermediate value in the encryption calculation by statically analyzing the data collected from multiple encryption operations. Correlation power analysis (CPA). CPA can be considered as a different form of DPA. This method is mainly based on Pearson correlation. It can be used to reflect the correlation between two samples, X and Y. Compared with DPA, CPA has many advantages, such as higher accuracy, and it needs fewer power traces. In our experiment, we choose CPA to attack Speck. The goal of CPA is to find the correlation between the predicted output and the actual output of the device. The steps of CPA can be simply summarized as below. First, encrypt number of n plaintexts to obtain number of n power traces. Second, pick an intermediate value L and make just key kg from 0 to 255. Third, for each just key kg, calculate the Hamming weight h of L. Then, calculate the correlation coefficient between power traces and h. Finally, if the correlation coefficient of a chess key is the largest, it is the correct key. The third part is method. Traditionally, when attacking the AES algorithm, the main attack point is the last round of sub-bytes operation. This box lookup operation will consume most of the power, so we can obtain power traces at this point. However, the Speck algorithm lacks the box lookup operation, so we have to choose another point to attack. In a side-channel attack, a good attack point is where the plaintext directly mixing with the key. In Speck, the plaintext directly mixing with the key occurred in the first XOR operation of the round function. So we choose the value after the first XOR operation as the intermediate value. The figure here shows the method of attacking the last round of Speck. In our experiment, we used Speck 128 as our target, so it has a total of 32 rounds, and the original key was divided into two words. The subscript numbers start from 0 in the figure. First, we run the Speck algorithm on the Arduino to generate the temporary value t at the round of 32. At the same time, we set a trigger signal and mirror the power consumption at the second XOR operation. After collected all power traces here, we need to establish a Hamming weight model. Here we set the chess key from 0 to 255. In our experiment, each attack is only for 1 byte of the key. One thing worth noting here is that the chess key here is not jazzing the original key, but the round key of the 32nd round. Because in here the plaintext mixing with the round key. For each jazz round key, it needs to do XOR with the temporary value t to generate a Hamming weight model of intermediate value v. These models represent the assumed power consumption. Then use these models with the actual power consumption we obtained before to run CPU analysis. If a Hamming weight model which corresponding to one of a just round key has the largest correlation coefficient with the actual power consumption, it means that the just round key is the correct round key of the 32nd round. Also, our method can be simply summarized as the following algorithm. The first part is experiment preparation and results. In the experiment, we mainly focus on the Speck 128 algorithm and use the 8-bit ATmega 3 to 8P based Arduino Uno as our implementation platform. At the same time, we use the Picoscope 2000 series to capture the power traces during encryption. Our experiment environment is shown in the table. Generally, in order to mirror the power consumption of the Arduino during encryption, some work needs to be done on the Arduino before the start of the experiment. Our method is to cut pin 22 and pin 8 of ATmega to 3 to 8P, connect a resistor of 51 ohm to pin 22, and connect the other terminal of this resistor to the GND pin, which on the Arduino. Then mirror the voltage across this resistor when the Arduino is running Speck. This voltage is associated with the power consumption of Arduino during encryption. In this experiment, we used 250 plaintexts start from O0. We generated it by adding 1 to the element sequentially until the ith element equals to FA, and we used the original key shown below. The figure here shows one of power traces. In our experiment environment, we found that the oscilloscope will be affected by many factors when capturing power traces. There will be some noise in the waveform, which may affect the accuracy of our experiment results. Therefore, we have to take some measures to get more accurate waveforms. Our method is to encrypt each plaintext 10 times separately and collect 2,500 power traces. Then use GNU Octave to average these power traces to obtain average 250 power traces. Finally, we use these 250 power traces to run CPU with the power model which we have established before. After key expansion, the round key of the 30-second round is shown here. First, we adjust the last byte of the round key 9F when running CPA. The result of it is shown in figure. It can be seen a significant correlation peak appears when the last byte of round key is adjusted to be 9F, which is the correct byte of the round key. Then we continue to chase the remaining 7 bytes of the round key respectively, and the significant correlation peaks appeared in all CPU results. The last part is conclusion. In this research, we proposed a possible attack method based on the structure of the Speck algorithm. By implementing Speck 128 on Arduino, we used the CPU attack to recover the round key successfully. Also, some countermeasures should be implemented. This will be our next research topic. That's all of my presentation. Thank you for watching and listening.